Okay, I have returned your assignment. Hopefully you look at it. Actually, this time the assignment result is quite good. Later we'll discuss about the solution, and if you found any that miscount or I misread your solution, you can come to me later. Okay. Right. So where did we left last time? So last time we talked about a few separation axiom. Okay, we talk about separation axiom. So what are the separation axiom that we introduced last time? You still remember? T0, T1, T2, T3, right? Also got T4? T4, good. So in between T3 and after T4 we have some special name, right? We have T3 plus T1 and T4 plus T1. What is T3 plus T1? Huh? Normal? Okay, good. Normal. T4 plus T1 is regular. Okay, good. So how do you remember this definition? Can see or not? A bit hard. Uh, yeah, never mind. I'm going to draw a picture now. Sorry. The other way? Which way? Regular and normal. Did we change way or not? Check, 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 check. Did we meet normal first or meet regular first? Regular first. Yeah, I think it's regular first. Later we have uh, so we met regular first actually. Okay. Yeah. So please be aware. Be aware of these terminology because in the exam we won't provide definition or theorem sheets for you, okay? Because you need to know how to use them. Okay, so if you don't know about the definition, you won't know how to use them. So you need to somehow memorize it. Internalize it. Okay, I wouldn't say memorize, but internalize. Okay, so think of a way how to remember this regular and normal. Later we'll introduce more property, and then through property, try and link why we call them regular and then why we call them normal. Okay, we will introduce more property so that you can know how to think about them. So what is T0? What is T0? How do you think of it as a picture? Huh? About 2 points that you can separate one from the other using a open set. Okay. Maybe you can only have one open set for one of them. Correct. But in T1, what is allowed? You could either have one, sorry, am I using a different color here? You could have one open set that separate the other point. Okay. For every point you can do it. Okay, for every point you can do it. Okay. T2, right? T2 is the Hausdorff, the familiar Hausdorff definition, right? So for every 2 point, you can find two open set such that the two open set don't intersect each other. Okay or not? How about T3? So I think we already take all the possibility for 2 points, right? So now we need to go up a level. So we need to be able to separate a point and a close set. Okay. So you can find open set around close set and around a point such that their intersection is empty. Okay. Then T4, how about T4? We replace the all the points to closed set. Okay. So we replace all the points to closed set, such that there's this two open set that separate the two set. Okay. Yeah. Okay. Right. Okay, good. So now we will prove a property. So let's prove some property. So the properties T0, T1, T2, T3, subsequently regularity, hereditary, and productive. So can you recall what is hereditary and productive is? What's a property, topological property to be hereditary? Okay, every subset. So every subset of a T0, T1, T2, T3, or regular, okay, then all their subsets are having this property respectively. Productive, eh? Okay, product of T0 is T0, product of T1 is T1, product of T2 space is T2, product of T3 space is T3, and then product of regular space is regular. Okay. Let's see. So we will do hereditary. Okay, we will do hereditary proof. Productive is left as exercise. Okay, so let's do a hereditary proof. So suppose X is Ti, okay, for I equals to 0, 1, 2. So for I 0, 1, 2, right, what things we are separating? 2 points. Okay, so we just consider a subspace with 2 points inside it. Okay, so let Y be a subspace of X. And there are 2 points inside Y. Okay? If there's only 1 point inside Y, right, there's nothing to show. Okay. So we consider if there's two different points in Y. But this two different point in Y is also in X. Okay, so these two different points is also in X. Since X is Ti, either T0, T1, or T2, then surely there exists two open set that separate X and Y in X. Okay? Separate in the way of T0, T1, and T2. Then what can you take for open set in Y to separate the same way? You simply just consider U intersect Y and B intersect Y so that they are the required open neighborhood for X and Y in, for X and Y in the subspace capital Y. Okay, so we just use subspace topology here. Okay or not? Okay, quite straightforward. Okay, yeah. How about T3? Okay, T3 need to be a bit different, right? Because T3 we need to care about closed subset, closed set and point not in that set. So now suppose X is T3, okay, and then similarly we consider its subspace, okay, and what? And let A be closed in Y. Okay, let A be closed in Y. And X is in Y, but not in X. Okay, we want to separate these two things. Okay, how do we separate these two things? So similarly, you need to use the property of X being T3. Correct or not? Okay. So how do you pull this element back to T3? A is a closed set in Y. Can you represent A using something in X? What do you mean by closed in subspace topology? What is open in subspace topology? Sure. But you can write A as a intersection of closed set in X with Y, right? Okay, for some closed set, Okay. So if I take a bigger set A prime to intersect Y to get this A, if X is not in A prime, then there exists open neighborhood, right? Because that separate X and A prime because X is T3. So the problem is, will this X be in A prime or not? Why? Say again? What are you talking about? I'm talking about the point X as X here. What do you mean by point is T3?等一下先。Point 怎么会是 T3？哦，大 X，OK。Why？ Why？ 我就以为我们要用 logic 嘛，我就以为 logic。So one point one closer in X. Unnecessary. Yeah. So why X is not in A prime? Good. Very good. You understand what Yiheng say? Because where we pick X, pick X in Y, not in A. So X is already in Y. If it is in A prime, then it is in A. Contradiction. Okay, so it cannot be in A prime. Okay. So obviously, X cannot be in A prime. For otherwise, X will be in A. Okay, contradiction. We pick it from a complement of A. So now, good. So X is not in A prime, and then A prime is closed in X. X is in Y, obviously in X. So we can take the property that X is T3, that exists a disjoint open UV that's separating X and A prime. Okay. So now, can you construct two open set that separate X and A or not? How? Then we simply take U intersect Y and V intersect Y. There should be disjoint inside the subspace Y. Okay. Yeah, no. You need to show up. You need to check up. So to check that you understand this, you need to verify. So you need to verify U intercept Y and V intercept Y are really disjoint in in where? In Y. Okay. Yeah. You need to really verify. Obvious, although seems obvious, but you need to know how to do it. Okay. Does it make sense? Got question? Question? Okay. So obviously regularity is hereditary because we already showed that T1 and T3 is hereditary. Okay. So productive or just leave as exercise. Okay. So you can see that from this proposition, what axiom I leave out? T4. Okay, so it is suggesting that T4 is not hereditary. Okay, so T4 is a bit similar to the compact property. So let's put it here. So the theorem is if X is T4, okay, and Y is a closed subset of X, then Y is T4. Okay, so you need to talk about closed subset, only you can bring the T4 down. It's a bit like the compactness, right? Compactness. Closed and compact is compact. Okay, you need extra property there. Okay, so T4 and normality are hereditary to closed subset of subspace, sorry, closed subspace. Okay, so try and so I think we will skip this proof as well. Exercise. Or exercise also don't know how to spell. Exercise. Okay, so you could imagine why we need this closed subsets. Last time we proved a problem property, right? Closed set, a closed set in a closed subspace is closed in the original set. Okay. So we are trying to use this line to bring the T4 down to the subspace. So so try in general, try and think about can you give example? Uh, try and give some example that T4 is not hereditary. Okay, and so and moreover, actually, it is also not productive. Actually, okay. Try see if you can give some example to this line. Okay, so T4 is a bit not normal. Okay, let's continue. Okay, so this theorem is quite important here because we give another characterization for T3 and T4. Okay, we give another characterization for T3 and T4. So just now we draw using separating closed set and point and also separating closed set. But now we will give some criteria for the how do you talk about open set inside here. Okay, so space is T3 if and only if for every X in this space, okay, then and every open set, okay, that contain X, meaning open neighborhood, okay, open neighborhood of X. There exists another open neighborhood V, okay, such that the closure of V is in U. Okay, how do you think about this? So for every point in your space, right? Okay, you have open neighborhood around it. Okay, you have an open neighborhood around it. And then you would have a smaller, correct? Smaller open neighborhood V living inside U such that the closure of this V also live inside U. So meaning between every point and an open set, there's a closed set. Not a closed set, maybe it's not closed, just that what after we take the closure. Okay? After we take closure. Okay. And how about T4? T4 is kind of similar. So T4, what T4 is for every closed set instead of a point A, and every open U in A that exists an open V such that this A is contained in V and contained in V bar, then V bar is contained in U. So instead of a point, you talk about closed set in T4. So this is another criterion for T3 and T4. Okay, remember what's the previous T3 doing? We have a point and a closed set, we can separate them. Okay? But now, if you look at the separation, the two separation, in fact, this dot is living in some closed set. E bar here. Actually, that point is living in some closed set, actually. Okay. How about this set? This content here. It says that between this closed set and between the open neighborhood, there's some other closed set. Okay, so we are gonna prove A only, and later you'll see that B is just replacing the A proof point become a closed set. Okay, later you'll see. So let's prove A. Let's see how we prove A. So let's prove one direction. Which direction? So let's go forward proof. So suppose X is a T3 space. Okay, suppose X is a T3 space. And then we need to show for all X and all open neighborhood of X, right? So we just take any point of X and any open neighborhood of X. Right. So what do you need to show? Okay, let's keep our goal up front. Want to show that there exists an open neighborhood of X such that V bar is in U. Okay, we need to find this V. We need to find this V using the property of T3. So to use property of T3, right, what do you need? About close. A closed set and a point, right? So now you only have a point. So where to find the closed set? Which open set here? Obviously, there's one choice you can make here, right? So if you let B equals to X minus U, obviously then B is closed. But is X in B or not? Or what? Small x, sorry, small s. Is the small s in B or not? No, right? Okay, so obviously the small s and the B is disjoint. Okay, so we can use T3 now. So by assumption, there exists disjoint open V and W such that V is containing X and W contain the set B. So you see, when I say contain, both way contain differently. One is contain point, one is contain set. Sometimes I say subset, I also say in. So you need to be careful what is in there. So is an element in there, or is a point in there, or is a set in there? So that's why I come up with the question in the midterm. Is an element of transitive or not? So what kind of in you are talking about? If it is subset of in, then transitive. If not, then maybe not. Okay, so you need to be careful. What in, what content what is very important. Okay, so good. So is this V the V we want or not? Hmm? Is this V the V we want or not? Why? Yeah, why? So let's do some working here. P closure is in X minus U, you say? What is W? Okay. Why is it true? How do you get this result here? Get this result here? W cannot contain limit point of V. The true? Why? Two several Okay, okay, okay. Sure. So you said that W cannot contain the limit point of V. Okay, sure, good. So since since V intercept W is empty, okay, the limit point of limit point of V cannot live in W, and then you want to show that this thing is living in U. Right? Okay, why this thing live in U? So somehow this guy need to live in U. X minus W is in X minus B. Okay, this is pretty obvious, right? Because you have an inclusion from B to W, so their complement should go the other way. Are we done? Yeah, so what is this? This one is X minus, what is B? X minus U. So this is U. Okay, good. How about the other direction? Okay, this is one direction. So from this proof, what did you see? The V bar we take actually is the V that we obtain from the T3 condition. Okay. Okay. So the other, how about the other direction? Suppose X and close set B not containing X given. Okay. From the other direction, what do you need to do? You need to produce two disjoint open set. Okay, you need to produce two disjoint open set here. But what you know is for every point, okay, and every open neighborhood that contain that point, you can find V such that V bar is living in U. But now I give you, instead I give you open set, I give you closed set, not containing X. So how do you create the open set that the question wants that contain X? How? Same way, take the complete U to be X minus B. Okay. So how do you think about it? So you have an X here, right? And then you have a closed set A, like that, right? So instead, you take the complement of A that contain X. Okay, it's open. Okay. So by assumption, what do you have? By assumption, there exists a open neighborhood B, okay, V of X, such that what? Such that V bar is living in U. Okay, such that V bar is living in U. So how to think about this guy here? Perhaps how to think about it? You can draw something like this, closed set inside U that contain X. Does it work? Something like that. Closed set live inside U, complement of A. Hmm? What is B? What is B? Oh, yeah, yeah, sure. This one is B. Thank you. The closed set is called B. I thought it's A. Okay. Okay, then what are the two open set that separate B at this point then in this case? Consider V and complement of V bar. Okay. Okay, so what do you need to check here? Sorry. Sure, check disjoint. So before checking disjoint, right? Does this two open neighborhood contain the thing that we want to separate or not? Okay. First of all, V contain X, obviously. X minus V bar contain B or not? How to show? How to show? How to show? So let's do some working here. So what we want to show? We want to show that A is contained in X minus V bar. Sorry, A again. B. Okay, B. So how? Wait. So what implies this guy? Maybe X minus B contained in V bar like that. I don't know. If I can get the second line, I think I should get the first line. Right? Why I write my U like B. Okay. But sorry, V has a VV. Sorry, thank you. A bit confusing. Okay. And then what is X minus B? Exactly U. So this is what we have. Okay. So we can go from this line here, and then we can infer that B is in X minus B bar. Okay. Okay. Okay, so exactly we are using this property here. Okay, good. So after containing what we want, are they intersect trivially or not? They're intersecting trivially. Or what is V intersect X bar V bar? Mm-hmm. Huh? Empty, yeah, empty. So why is it empty? So this one is empty since V is inside V bar. Okay, okay, good. So not that we didn't really quite use the property of this X here. We didn't have any extra info, I mean assumption on X. What we play around is just whether we can separate this point and a closed set or not. So the whole proof here, right? You can replace this X with a closed X, closed set X. And then the whole proof works similarly. Okay, because the difference between T3 and T4 is just separating whether a point and a closed set or two closed set. But the way to separate them is the same. I have two open set that have disjoint intersection, no intersection, separation. Huh? Yeah. Okay. Okay. So far, any question or not on this two thing? Any question? Any question? No. So far, so okay. Okay, still okay. Still okay. Can go on, or do you want to take a break? What do you think? You want to go on? You want to take a break? I think we just discuss one very heavy thing, and then we go for assignment. You want to challenge yourself, or you want to take a break? You are the spokesperson. You want to do very challenging stuff and then break, and then we discuss assignment, or challenging first? Okay, ready? Ready your mind? I see 1, 2, 3, 4, 5, 6, 7, 7 page of proof. Okay, let's see the statement first. Okay. This I think later no time already discuss the assignment. I said no time already. Yeah. Huh? Take a nap first. So we prove this very long proof in not just this one. We still have more long proof. So there are more long proof about a recent metrization theorem, Pekanov theorem, and then Ascola theorem. This three things we finish, then we finish this course. Okay. So this is the first very super long proof you will see in this course, which is called the Uryshon lemma. So what is Uryshon lemma here? So it says that a space is normal, okay, if and only if for every disjoint. Remember what is normal? T what? T4. Okay, T4 plus T1. Disjoint close AB. So T4 talking about separating two close set, right? So we have two disjoint close set here that exists. This is the main thing different already. So this is a continuous map. Okay, continuous map from this normal space to the interval 0, 1. The interval 0, 1 here is not very interesting. You can put it to any close interval. If you can reach here, then you can basically reach all the close interval already. Such that fx equals 0 for all x in A, and fx equals to 1 for all x in B. So what am I doing here? So for these two closed set, I send one subspace to 0. I send the other subspace to 1. But the condition here is this function is continuous. So everything in between A, B, I can somehow arrange it such that my function is continuous. Somehow. This somehow constitute 7 page. This somehow. It's many how, not somehow. Many how, not just somehow. Okay. Okay. Why is it long? Because it's very constructive. Very constructive. Okay. Very original idea. Actually, one direction is easier. Do you reckon one direction is super easy? Which direction? Left to right. Left to right is the one that involves construction. So it's pretty hard. Right to left. Okay. Right to left, why is it easier? Because I already construct for you. I already give you this F already. So what you need to do is you need to, for any two AB, give me the disjoint open neighborhood. And give or not? How to give? How to give for the other direction? For the other direction, how? What do you need to show the other direction? What is normal? For every two disjoint closed set, you need to find two disjoint open neighborhood. So let's say for every two disjoint, you got this function already. How to find the two disjoint open neighborhood? Yes. So you just look at the pre-image of 0 to 0.5 that contains A, and the pre-image of 0.5 up to 1 that contains B. Okay. Surely these two things have intersection 0. I mean empty. Okay. Otherwise, it will have value inside the same range. Okay. Why A is in here? Because A is the pre-image of 0. I just had extra stuff. If you want to take until 0.25 also can. Correct. Okay. But here, this one is the pre-image content 1. So B is the pre-image of 1. So this two sets should be empty. Why? Otherwise, you will map to the same image. Okay, otherwise you map to the same image. Okay, this is just a basic set theory why they have to be empty. If the image is, I mean the intersection of the image is empty. Okay, this is basic function only. Okay, the other direction. Let's see what time is it? Hey, your question, yeah. No, no. Wait. So A union B is not X. Yeah. So do you agree that A is inside this inverse image or not? What's the definition of inverse image? These are the all things inside X such that Fx is equals to, okay, not equal because we have a range here. So Fx is in the range of 0 to 0.5. So you ask yourself, if is Fa living inside this range or not? Yes, right, because Fa is 0. Yeah, this is the definition. This is the definition. Pre-image, okay, inverse image. Okay, okay, everyone, good, makes sense. Yes, we purposely miss it out. Otherwise, there will be intersection maybe. So I will throw away. If you like, you can put 2,5 here also can. Two disjoint. Two disjoint. If I include 0.5, then maybe not true already. Maybe not true. Okay, so I purposely make them disjoint. Okay. Yeah. Okay. But I need of course I need some open set. Okay. Because this one is open in the subspace topology, so open. Don't take some close interval, otherwise your pre-image. Uh, let me think. You need to take within this range. Within this range. Within this range. Yeah. Okay. Yeah. Just make sure it's open inside your space. Because it's continuous, okay? Inverse image is still open. Jujian come at the right time. We're about to do the super hard proof in the general topology. Okay. After this proof, we'll take a bit long break. Not just you want to break, I also need to break. Okay. So let's start. Be ready. Okay, see if you can follow what we are trying to construct here. So keep in mind, what do we want? We want to construct continuous function. Okay, yeah. Before that, yeah. Oh, have we proved T1? Right. So how to prove T1? T1. Let me see. T1 is about 2 point, right? Let me think. Sorry. Yeah, so the question is, can you apply this statement to points? This statement to points. We apply this statement to point for any 2 points. And what is T1 again? Every point have one over. Yeah, correct. Let me see. What about T1? How about T1? Let's think. So should that point living in one? That 2 points should either live in some closed set or either they are closed by themselves. Can I say like that? How about 2 points? Can I say that 2 points either they are closed as a 1 point set or it should live inside a closed set? So the problem is whether there's a two historical set or not. About T1? True about T1. 1 point set is closed if and only if it's T1. Do we just have T4 here? Let me see. Normal, we have normal. One direction we should have normal. How about the other direction? Can we prove normal? Direction we have normal, the other direction should we have normal? Surely it's T4 already, right? How about T1? What do you mean? T4 cannot imply T1, right? That's why we add the T1 and T4 together to get normal. What do you think? Hmm? Yes. No condition. No condition here. No condition about host number. Did I miss anything inside this statement or not? Did I miss anything in this statement? Let's check the textbook. Anyone have textbook with you? What's the statement there? I think I just add one direction into that statement. Yeah. Mm. Mm-hmm. Mm-hmm. Yeah, it's the same, right? It's the same. So how about the other direction? Where did I get the other direction? I get from Richmond, I think. Let's see, did I copy down something? That's Richmond separation. So it's page 163. Let's check if I leave out any condition on. See, yeah, textbook is not even only, but you can deduce the other direction, but I'm not sure. Seems like we cannot do T1. So I think maybe I missed out something. Let me check on. There's a if and only if direction if you write it. Did I miss out anything or not? Ah, okay, I did miss out something. T1 is not implied, so I need to add it in. So if I want this direction, the other direction to be true, I have to put T1 in. It cannot be implied because unless you know that your 1 point set is closed. If you know that your 1 point set is closed, it's exactly T1 already. That's mean I already put inside the put in the property. Okay, so if I want to, if I only if, then I need to throw in this T1 property here. What? What? The back, the backward need T1 because it's not implied by this continuous map. It's not implied, so we need to throw it in. But the forward, you need a normality. Okay, okay, yeah, okay, good. So I think we can do until let's set a time. 1:15. Okay, hopefully we can finish by 1:15. Yeah, you ready? Yeah. So we split the proof into few step, 3 step. Okay. Maybe we won't go into super detail for some of the parts. We would just sketch roughly. And for the full proof, you can check out Moncrief. Okay. So let's split into 3 parts here. So step 1. Okay. Remember, what do we need to do? We want to construct a continuous function. Okay. So let's see how we construct this function here. So first, we will use normality, okay, to construct a certain family. Okay, let's call it UP of open set of X. Okay, and then we will use rational number to index them. Okay, indexed by rational number. Okay, to define the continuous F. Okay, so to define continuous F, we know where I'm going to send A already. I also know where I'm going to send B. But what about other points? So we use this series of sequence of open set to define it. Okay, and then once we define the function, we need to check that the function is actually continuous. Okay, so this makes things a bit hard. Okay, so how we make this series of um, open set here. Note that I specify that I want to index by rational number. So what's rational numbers trying to do here? We're trying to use the density of rational number later. Okay, right. So first of all, what do we have now? Okay, we have two closed sets. So maybe keep some picture in our mind. I think is a good idea. So let's keep a closed set A and B here. And what we want to do is we want to map it to a closed interval. So 0 and 1. Okay. So we map everything in A to 0, map everything in B to 1. But you still have something outside. So what we're gonna do with the thing outside here? Okay, so this is the problem. So what we can do is we can set u1 to be x minus b. Okay, why we set this? What is x minus b here? Yes, good. It is open. And also, this guy here contains a okay open set that contains a closed set. The previous theorem says what? When your space is T4, things X is T4, there exists a open set such that A is in this open set and also in its closure such that this closure is in U1. Okay. So what have I done here? What have I done here? I look at the complement, okay, and then I cover this A, right, using a slightly larger closed set. Slightly larger. Okay. Does it make sense? Okay, good. Good, Okay, good. Then what's next? Okay, what's next? You see, let me be careful a bit. So we are about to apply this this process inductively. So how are we going to do this inductively? Yes. Okay. We cover A using a slightly larger closed set, huh? But you should realize that this closed set and B should still disjoint. Okay, still disjoint. So again, applying the preceding theorem to U not bar and B. Okay, and then we will denote this new open set as U half. Okay, so where does U half live? U half should live in between U naught and U1. So meaning what? I go one more step further. So can you see how I'm trying to approach this B? I try to get larger, closer. Okay, so I keep doing this. And then, so inductively, let me don't write the step down. So the very detailed proof is in one crease, and then I summarize the proof inside my note, so you can try and read two together. So inductively, what do you get? You get something like this. Okay, actually you can increase on both sides. Okay, on both sides, you can keep um filling in the step. Okay, you can fill it in on this side here, okay, you can also fill it in on that side. Okay, you keep filling in. Okay, so you keep doing it. So what have we done here? So the first step, we add in all the 1/2 labeled open set. In the second step, we add in all the 1/2 to the power 2 label. Okay. And then next step, we will add in all the 1 to the 2 to the power 3 label. And then 1 to the power 4 label. Keep adding it. Okay. Does it make sense? Make sense or not? Got question? Any question? Okay. So we keep doing it. Okay. What about why are we doing this? I haven't tell you why are we doing this. So why are we doing this? So continuing in this way, what kind of open set we get? So the open set we get looks like this. U r such that this r is living in m/2 to the power n. Okay. We'll get all this number. Let's call this set D. Okay. Why this D is important here? This set D has a name. Okay, this D set has a name. It is called the set of dyadic fraction. Okay, and in particular, this set is dense in 0, 1. Okay, later we're going to use the denseness of this set. Okay. So the very important thing is, very important things to keep in mind here is, so for out of this construction, what do you need to know? This is the only thing you need to know. For P and Q less than D, we have A in U0 is in UP, and then UP is in UP bar is in UQ, and then UQ is in U1, like this. Okay, this is the very important thing that you need to know from our construction here. For every two number, you can compare which one is greater and larger, and then the open set is following this include this order. Okay. P contained in UQ, the UP contained in UQ. Okay, so we have got this set here. So we need to define a function. So how do we define this function? Okay, how do we define this function here? Okay, how do we define this function? So this function will be defined like this. So let's define a function from x to 0, 1. Okay. So obviously, what do you need to do if x is in B? Okay, we know where we want to send this point to is 1. Okay, but if x is not in B, what do we do? Okay, so this is the trick here. So what are we gonna do if x is not in B? Okay, we send it to the increment of R such that R is in D and x is in UR. Okay, so what do we do here? I send to the number that label the open set containing x. Not just the number, it's the smallest number. Smallest number that contain x. Not smallest, infimum, maybe not achievable, correct or not? Okay, infimum. Look at the limit. Okay, limit of all the open set that contain this point. Okay, can you imagine or not? Because in A, right, outside A, maybe after a certain open set, it won't contain that point already. Okay, so you look at limit of all open set that contain that point, and then look at the infimum of all those index. Okay, so actually quite trouble, right? If you want to show this kind of function is continuous, you want to show this is continuous and like that. Okay, construct is easy, but how to see this guy is continuous? Yeah, so you can see that if your point is in A, that means you are in all the UR. So the infimum is 0. Correct or not? So it does satisfy that FA is 0 and the FB is 1. But the super hard thing is to check why this guy is continuous. Okay. So it should be easy to see FB is 1 by construction and FA is 0 because A live in all the UR. So yes, yes. Where the U0 come from? Good. So this is the first step. First U0. Hmm. I think. No, we already fixed this U0 already. So I mean, you see the further UR we make is containing U0. So we are not going the other direction. All right, because every point not in B should be in the complement of B, right? So everything in X and U0 also live in the complement of B, right? So every point, yeah. No, I mean those point may be evaluate to 0, but not very important. As long as I send my A to 0, I'm good already. I send a little bit more people go to 0 also can. Correct or not? No need so precise one. Because I just want my A go to 0 only. Other thing also can go to A, but just not the B thing. Correct or not? Ah, yeah. Make sense? Can go to 0. Actually, U0 should go to 0, right? The thing in U0 should go to 0. Yeah. So not just FA is 0, FU0 is also 0. Okay, yeah. Huh? Okay. So the last very hard part is to why how to see this guy is continuous. So how is to see this guy is continuous? Why F is continuous? Okay, need to see why F is continuous. And then once this is done, then we are done. Okay, why F is continuous. Right. How to see F is continuous? Consider any open set. Image is open. True, true. I was like thinking what I'm writing here. Uh, yes, you're right. You're right. Okay. So we can rephrase it this way. So let's set a x in x. Okay. Obviously, fx should live in some number between c and d, maybe. Okay. So what we want to do is we want to find a pre-image, right? So I will write it as u. Okay. Open around x such that this pre-image map into the CD. Okay. Yeah. You look at some open neighborhood, epsilon over neighborhood around fx. Again, you want to find some delta neighborhood such that you map all the delta neighborhood into the epsilon neighborhood. Can? Okay, so this is our job here. So what to do here? So here we're gonna pull out the density of our dyadic ratio here. So choose M1 over M1 and M2 over 2 M2. How are we choosing here? So you can think of it as fx is here, okay, d is here, c is here. So how do we control this number? This number is quite random. We cannot control. But we know that our dyadic number is dense. Dense means what? Any two real number, then I can find one of them between them. So between c and fx, I can find some dyadic number here. Okay, between fx and d, I can find another dyadic number here. Okay. So how do we find this u then? How do we find this u? How do we find the u? The claim is u is equals to u m2 2m2, take away the closure of u m1 over 2m1. This is the claim. Okay, so this is the claim. Okay, this is the claim. So how do we prove this? So if we want to claim this, what do we need to show? First, we need to show that x is actually in this neighborhood. And then f of this neighborhood should be inside CD. Okay, two things. Yes, two things to show. So first of all, why x is inside here? Yeah, why is it x is inside here? That fx is less than m2 over 2m2. Okay. This is enough to imply that x is living in um2 m2. Why? How do we choose fx? Infimum, correct or not? So infimum of your x, the open set is already less than this number. So meaning you must at least live in this open set so that you can achieve lower down. Okay. Second of all, since fx is greater than m1 over 2 to our m1, then x shouldn't live in the closure of u m1 over 2m1. Okay, why? The infimum that this guy live in is already greater than this number. So you cannot live in this open set and also the closure. Yeah, why not the closure? What construction is that? So otherwise, if it live inside there, what happen? Meaning fx will be less than or equals to m1 over 2m. Okay. If it live in the open set, then your infimum should go lower than this number already. Equal, lower or equal to. Okay. So it cannot live in the. Okay. I mean, you need to come back to this line. Okay. Okay. Next. So next part, second part is to show that you live inside CD. Okay. Why f of this thing live inside CD? So let's take any point inside our chosen U. Then if x is in a U of M2 over 2M2, what do we have? We have this guy living in the closure of 2M2 M2 over 2M2. Okay. So what does this mean? This means what? What can you talk about this fx? Hash where? Huh? No, we take x in U now. Hey, by the way, we are not implying M1 is the same. So I think this one is a different, and okay, we can take a random combination of these two number. Okay, we take random combination. Okay, we don't restrict ourselves to the same number. We are taking random combination about these two numerator and denominator power. Okay, right. So where's the notation clash? This x here is referring to any point in U. Okay. So if x is inside this set, this means what? This fx is the increment of all these numbers, right? So it should be less than or equal to the index here. Okay. But this index here, we know that it's less than d. This is how we pick M2 and 2. Okay. And secondly, you can see that if x is not in the closure, what do we get? If it is not in the closure, it is also not in the open set. Okay. So this would imply that it is not in all the number that is less than M1 over 2N1. So this would imply that fx is at least greater or equal to M1 over 2M1, which is greater than C. Okay, so altogether, we will imply that fx is living inside M1 over 2N1, comma M2 over 2N2, and this whole thing is in C. Okay, does it make sense? Okay, so by the way, we didn't check at the endpoint, but endpoint is similar. You can check at the endpoint similarly. Endpoint at 0 and 1. Did we exactly touch? I didn't say wait even if it doesn't touch, right, I also can put the close sign. I don't know, even if I didn't touch, I just need to show that it is inside this range. But the problem, if you want whether it touch or not, whether it touch or not, let me think. I think depends, depends on your set. Depends on your, depends on your set. Whether it touch or not, I think it's depend on cases. Mm. Yeah. But fx can take infimum, or you need to remember infimum. Like 1 over n, you never touch 0, but infimum is 0. I don't know. Yeah. But I mean, what if I put closure, put closed interval here also never mind if it doesn't touch, because I just want to say that this number is living inside this region here. And then I make sure that this region is living inside CD. This is how I pick these two numbers. Maybe can reach sometimes, depend on your open set, depend on your space itself. Okay or not? Yeah. So this is quite important. Later we'll use this. Okay, how to separate two set using continuous function. Okay or not? Okay. 10 more minutes. Okay. Okay. Any question about this? So what I want you to appreciate is first, how we define this function. Okay, to define this function, we use the sequence of open set, which is dense. Okay, and then why I need the denseness? Because I use the index to get my value of f. Okay, and then use this to show that it is continuous. Okay, so the brilliant thing that happens inside the whole proof is use the normality first of all. Okay, second of all is come up with this function here. And this is the two main construction. Once this construction is done, what's left is just checking. You just check. Moncrief's one is super long. Why do you know it is super long here? It doesn't make a precise choice of a dense number inside inside the interval. Okay, he used random dense function so that he need to do formalization, more technicality, more technical point. But here, in the Richmond, they just pick a specific one, a specific dense set inside the. Yeah, I need to show that I think it's there. I think that one is should be easier to see, right? Quite easy to see, right? Yeah, it should be quite easy to see. I mean, how to say? Can you use a few times of Archimedean thing? You should be able to use few times of Archimedean property, then you should find a natural number. Yes, or? I don't know. Hmm? Yeah, so if you are worried, you can show that why the big number is that side. Okay, so let's take a break. Break until 1:35, and then we can discuss assignment. Go up, down, down, down. Okay. Okay, 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 okay. What else 你要 check 吗 What do you want to check? What else you want to check? What else you want to check? 就是那个 function。我 define 那个 function to take the value of the index of 那个 open set。因为 dense 用在这一步，在这一步，我要 show continuity 的时候，我要怎样去找那个 pre-image？Yes, yes. For every epsilon, you need to find a delta. 所以怎样去找的 delta？因为没有好控制的话，控制不到这个。Yeah. 哦，我用那个 那个 index 来控制哦。U 就是那个 pre-image 啊。哦，你是说 show that pre-image is open 哈？是不是意思？是这个意思？这有一点这个epsilon delta proof 哦，epsilon delta proof 对不对？ fx 在 CD 嘛，一个 epsilon neighborhood 嘛，there is a delta 啊，这个 U 是那个 delta neighborhood，呀呀，你要找的那个是比较大的，是不是？比较大的，因为 from 我们的 construction，我们不一定找到准的嘛，因为 C 跟 D 不一定是 dyadic 号码嘛，不一定是 dyadic 号码，so yeah。因为我们在 define 这个 pre-match 的时候，我们是用这个 dyadic 这个 open set，我们 open set 是 label by 这个 OK。那我们这个什么 PPT 啊？呀，一条人对，一条人。就是你可以 separate 两个 disjoint open set 用 function。对，later 我们会 introduce 这个 definition。这个 argue 嘛，会有没有这个东西的？我讲了。是不是如果你就没有 pop 出来这个 continue 这个 lemma 的话，那就很长，你就知道这个稍微可以有一个对。I mean yeah。说这个东西跟那个 back home 讲的东西有关系耶，back home 这个东西要做你讲的那个东西啊，你知道吗？哦，就是说为什么 destroy 他们两个之间有距离？哎，这边我们还没有分两个 open set，我们现在在分这两个 destroy 的 close set，他们两个有距离哦，现在有距离哦，哦，但是要是 normal 先啊，但是 normal implies full stop 对不对？我们上次讲过错了，the other direction，the other direction，the other direction 很强耶，normal，看一下记一下这个 direction。is the direction 啊，normal 很给。对啊，你看这个，后时候在中间罢了normal 差不多什么都有了，因为 normal 加 T1 讲 every one point set 是 close，所以 close 又丢去 destroy close set 那边了，所以你什么 destroy close set 都给你分掉了，one point set 也给你分掉了。对，但是 normal 有 T1 在里面，T1 把 one point set 变成 close set，好吗？因为我们 prove 了，你看 T1 if and only if singleton is close，所以把所有的 one point 的全部变成 close set。Then T4 告诉你什么 close set 你都可以分，then 你连 one point 也可以分对，是这个意思。对，所以刚才我们在纠结这个问题嘛，刚才那个如果有 continuous function 到底有没有 imply 那个，但是我不知道 close one point set 到底 close 不 close 嘛，所以我一定要让它 close 先。T1。对，哪一个 lemma？从左到右没有，从右到左要，右到左要啊，因为我只能够，如果那个 continuous function 出现，我只有 T4 罢了，我没有 T1，也做不出 T1，因为 condition only on this point so set 除非我知道 open one point set is closed，如果我知道那个是等于什么意思，我就把 T1 丢进去了，对不对？其实你的 T4 就看其他的看他们 T4 是在教很多的，T3 有个很多哪一本书？对在书里面有讲说有些人没有把 normal 跟 regular 放进 T1，但是至少我们看那个 matrix 跟 Richmond 都有，所以我们就有，所以要 check 好 convention。我们这个 class 有。 买两本书都有
区分的。
有区分，
有区分那个
有区分。那有区分有区分有区分。刚才我一 recall 的时候就开始区分了。对啊，我 recall 的时候就。哪一本书？哦，有那本书有那个我 miss out 掉。我在看两个东西的时候我 miss out 掉。Richmond 有写T1 space is T4。所以我 miss out。就可以，就可以。哦，就可以。T4的我跟你就也是。没有，我 miss out 我 miss out。没有，不直接啊。那就书。但是我觉得什么没不懂，至少主流的书好像都是要有提问在去包装那个黑的。主流你有一些直接把题目这样弄吗？有，他书有讲有人这样子做，主流是有，通常 normal 跟 regular 是这样，那不然的话不是很奇怪，不奇怪的，很奇怪的。一些小东西你分不了，就可以分大东西，对不对？那是把 1.7 T4 include 把 T1 include 进去 T4 里面。对，T 对，就说假设你是 T4，但是不 T1 啊，不是 T4 你 include T1，大家听下哦，所以 OK， 你那 case 也是一样的咯。但是我想讲的 case 是有些人没有，就是 regular 跟 normal 就是 T3 跟 T4 没有 T1 的，没有你不 T1 进去 T3 T4。也没有啊。就是我刚才讲的，T3 没有 T1，但是它叫 regular。但是我们在讲的是T3 直接有 T1 在里面了。这个是这样不一样哦，这样跟我们一样哦，其实跟我们一样哦。只是说你没有单单讨论 T3 嘛。对，没有单单讨论 T3，把 normal 跟 regular 还是一样，对。一样哦，这样就一样。regular 是一样，但是没有讲纯 T3。这样就一样，我讲的 version 是。它有 T3，但是没有 regular， 但是还是叫 regular。Okay, maybe we can discuss a bit on the assignment, then we will break. Six. Actually, this time the assignment result is quite good. Average hit about 80. Yeah, the standard deviation decreased a lot from 20 something decreased to 8. I think it's very good. Huh? What? Seriously? means 80，然后standard deviation 全部东西会给老师。什么意思？没有了。80分，然后区间是就这个意思吧，就是大家不会距离得很远，然后大家又挤在蛮高的分数线上，就这样吧。我没有叫你背 formula， 不要怕，不要怕，我没有叫你背 formula， 我也很怕那个 formula。我只是想看大家距离多远，还有 like average 在哪里吧。Okay, but I mean this is the right way to do assignment。我看到你们有用心，虽然当然可能有写错一点东西 ，but 我有看到你们的用心，so this is very good。所以你就是应该要用这种 attitude 去做，你们就是每一个 assignment 都要这样做，不只是我的吧，全部都是要这样做。OK 好的 ，OK。So we'll discuss solution and then try check whether how different is your solution and then whether I mismark your solution or not. Okay, so the first question, first question, we want to show connectedness for this set here. This set is what? It's a subset of R2. Okay. The condition is either X or Y is irrational. Okay, can be both. Can be both irrational. Okay, either. So what I do here is I suppose A1 is irrational first. Then either B1 or B2 is irrational. Okay. So without law of generality, we assume B1 is irrational. So to show connectedness, right, either you use separation or you use path connected. So in this case, it's in R2. So maybe it's easier to use path connectedness. So I will just make a path in between these 2 points here. So you have an irrational A1 and an irrational B1. So how do you make path between them? Some of you straight away make path, straight line path between them. But how do you make sure that the path you take is living in X1 and in X? You can't make sure that. Okay. So what you do is you take A1. Okay, so let me put irrational on both here. So first you should build a path from A1 irrational to something really irrational in the second set, maybe something like that. Okay. Then then only you change the first one to B1 irrational while you keeping the other coordinate irrational. Then for sure you're always living in X. Only now then you can map your path to B irrational, B1 irrational, B2. Okay. Okay. And then if you want to show the formalization, how to make this into a real path that define from 0 to 1, can. If you don't do it, it's fine because we already discussed in class how to compose two curves into a proper path. Okay. Yeah. And then you can discuss other cases as well. It's similar. Okay. So this is how we make sure the whole path live inside X. Okay. Some of you just just make a straight line. So no, not appropriate. Okay, any question on question one? Okay or not? Question one. Okay. Okay, question two. Question two asks you to prove that this function, continuous function from 0, 1 to 0, 1 has a fixed point. Fp equals to P. Have a fixed point. Okay. Is a fixed point an important subject in fractal geometry or not? Or not fractal geometry, you call it a dynamical system. Very important, right? Fixed point, whether it has a fixed point or not. And then if it has a fixed point, how to approach that fixed point. Fair enough. Okay, good. So this question here, a lot of you use intermediate value theorem. I didn't realize you, but I hope after this assignment, you should learn how to use connectedness argument. Okay, because in the exam, we will use connectedness, compactness. Okay, you have to know how to use connectedness ideas here. So how to use connectedness argument in this case? What we do here is we realize this graph. Okay, I cannot say realize this graph. I realize this function as a graph in R2. Okay. And then you can form this y equals to x line here. So let me draw it. Y equals to x line here. Okay. Like what I said in the class last time, away from this line, so here is y greater than x, bottom is x less than y. Okay. Correct. Correct, right? Which one? X larger than 1. Oh, what are you talking about? I'm talking about the region away from y equals to x. This region and this region here. Say again. X larger than 1. Y larger than 1.
X larger than y. It means y is less than x. Yeah, y is less than x.
For this part, this part is y less than x. Then this part is okay. Oh, okay, good. Okay, thank you. Okay, so what I want to argue here is this two set here is open. Okay, this two set is open. So because there's no point, okay, no point around y equals to x, so you need to use a contradiction argument. So suppose there's no fixed point. Okay, so there's no value of x that take points on this line. So meaning you can use these two open set to separate your image of fi. But can you separate your image of Fi? Why not? Because Fi is a continuous image of a connected set. Must be continuous. Must be connected. So you must somehow meet this line here. Once you met the line y equals to x, that's the point that give you f p equals p. P is the intersection. Is the intersection. Does it make sense? Make sense or not? Okay. First of all, you need to make sense what I say. Second, you need to know how to write out what I say. Okay, so this is the two things you need to do in this pure maths class. Okay, one is understanding the concept. Two is to write down the concept. Okay, if you miss any one of this element, then you will miss mark. Okay, if you write, but don't know what's the concept, then you're wrong. If you know the concept, but you cannot write it good, you also cannot get full marks. Okay, so you need to do these two parts. First, you need to know the concept. Second, write down the concept. Okay, so these two things you need to execute. Okay, so you need to learn this connectedness argument. Okay. Any question about this solution or your solution or not? Okay. Yeah. Come on. Later. Okay. Okay. Later. 等一下. Okay. Question 3. Show that the cofinite topological space is a compact space. Okay. So most of you do it well. This one you just need to use the open cover definition. And some of you even consider the case where only the empty set and the whole space is open. But you don't need to consider that. If you only have these two things open, right? This is what we call a indiscrete topology. So it's not cofinite already. Okay, so that one you can leave out. Safely leave it out. Okay, safely leave it out. So you could safely assume that there's one set where the complement is finite. Okay, you can straight away use that. Because the case you consider is an indiscrete topology. Okay, so you can simply ignore that. I didn't take mark, I just want to comment about that. So if once you have this complement of that particular set is finite, okay, then what do? You start with an open cover of X. If it is an open cover, then surely there's some element in this open cover that cover these finitely many points. You just need to take finitely many open set that contains them. Then what's left with is the first open set. How to cover that open set? Just add it in. Okay, just add it in. Okay, so these are the finite subcover that you want to create. Okay, 4. So you have a compact set, okay, and then there's a point not in that set such that there's two open set that separate each other. Actually, we did this in class. Do you realize? Do you realize that we did this? What kind of proof we did is similar? Yes, close in compact. Yes, exactly. That's the technique of proof used here. Okay, close in complex. Yes, that's right. And then this space is what? T what? T3. T2 is given, right? But what we show here is T3, right? Point and a closed set. Point and a closed set, and then we separate them. T3. T3 property is. Okay. And okay, last one. This is the hardest question. So you have a metric space. Then isometry. I think we saw isometry a few times already, right? In the assignment, in the exam. Okay. Now I want you to prove that fx to x is an isometry. Suppose that f is isometry, and if the space is compact, then it should be surjective. Okay. In the exam, you already see that this isometry might not be surjective, although it has to be injective. By what argument? Matrix, right? The definition of matrix. Okay, it have to be injective, but might not be surjective. But once I add compactness into it, it becomes surjective. Okay. Yeah. So how to show it? I think you guys get the right idea. So if you follow the construction that I gave you, that you define that a sequence of points by applying x to a certain x. Okay. Then what do? Because our space is compact, right? Okay. Because our space is compact, and you map x back to x. So the image of f is still in x. Okay. And then what? And then the hint says that you need to show that actually this sequence has a subsequence that converges to x. Okay, so this is what I show here. Okay, what I show here. So first show that for any x, there is a subsequence of x and converge to x. Actually, that how do I say that? Actually, the sequence that built out by the image of x, I mean inductive sequence of inductive image of f. Okay, cannot say like that. Inductive image of f on x has a subsequence that converges to x. Do you understand what I said now? So you go to x, right? Then you apply x, f f x, f f f x, f f f f f x, f f f f f f f x. And then somehow this sequence will have a subsequent converge back to the original point. This is what I asked you to show here. Okay, so how I did it? By contradiction. Okay, not by construction, by contradiction. If you cannot do it, then there will be some contradiction happening. Contradict what? Should be contradict to compactness. Okay, yeah. Because you need to combine with the property of isometry. You need to combine the property with isometry. Okay. Yeah, I think the solution is here. You can read about it. But the idea is similar to what most of you do. I think some of you have a shorter solution, should be okay. It's quite similar to what you guys did. But you can try and read how this contradiction being written. Okay, if you don't understand, then we can discuss. And then lastly, is this conclusion true? And most of you say not true. Actually, it's true. Actually, it's true. So there is a metric space X such that X is isometry to a proper subspace of itself. Okay. Why? First of all, there's a bijection between R and 0, 1. So what I want to do is I make this an isometry. How to make this an isometry? I use the simplest metric on both sides. Should be isometry. If you have a same point, the distance is 0. Different point is just 1. X to X is not surjective. 我都没有 X to X。我是说 there exists a bijection between R 跟这个 interval， 天然给的。嗯哼，我没有讲 false， 我讲 true。对，但是它不 compact 吗？wait let me see。你讲什么？你讲什么啊？给我想一下，你讲什么？ 然后我想一下你讲什么东西，再讲一次，再讲一次。来，是有两个，f(x) 等于 x，
这是 A 的口。而且你要给修那个这个 F 是 isometry 什么？
是 是 isometry，然后你来讲一次，再讲一次，什么 constant，慢慢来。呀，嗯，OK，我们想要证明什么句子之数？就是说，嗯，假设我们 space 不 compact，if f is not compact，can f be surjective？ OK，我们想一下有没有等于 x 啊？想一下啊，对，没有错，对，没有错。但是我们现在要 claim 的是，我们现在要 claim 的是，呃，其实 r 是等于01。OK，要讲它等于哈，嗯，let me think，呀，怎样的等于法哈？等一下我想一下，所以你是说它的 statement 有一点 rephrase 到不是很好？我想一下，就是来等于在这个世界我们要怎样的等于？我想一下，
没有的，你 A 不是你是 suppose F 是 X 和 X，那在我们那你的给的 example 是 R2，
对对对对对对
X 和 X。
对对对对对，但是我觉得他这个答案 somehow 要 claim 这个东西。等一下啊，要讲 phrase 这个东西。
那你看那个 example FX 和 X，我知道这个是对啊，但是 FX 和 X。
呃，对，等一下你给我想一下，
这也是对的。
这是对的呀。等一下我想一下加零去你刚才讲的东西，因为题目问 fx to x 嘛，因为我 somehow 在想 x 跟这个东西是一样的，所以这个一样呢要怎样把它放进去来解释？呃，我想一下
这等于是 FX 和 X，
啊
不是同一个，那同一个。
啊，对对对对对对对对对对对。假设我这个可以去到这里的话，哎，sorry sorry 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 sorry，
我要找啊。
嘿，sorry sorry 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 sorry，
有人要进来的。
哦，OK，没问题，sorry sorry sorry，OK，tomorrow we discuss again。
因为没有这种所以说我自己弄一个。我们讲 X 要比零，我是讲我把这个 sequence 对吧？
OK，等一下啊，我们 们要用麦吗？
不要吧，不要啊！
不要了，不要了，
小娟要用麦的，
不要了，不要了。
你这些几个人？
确实，就几个人。你朋友没有来啊？
朋友谁？没有朋友，我朋友是谁？
重要的。
他来我就走了，不是开玩笑。他来我就回去了。
在哪里啊？
我觉得我讲很好吃。
你要放假了是不是？OK，
是啊，好像是。好像还有那个什么，那个零贴上的还有，
这个还没结束。
我们这个男人
啊，